This video is going to demonstrate how to use the factor theorem to first find a factor by trial and error of this cubic polynomial, and once we have the first factor, then long division using the polynomial to find the other factors. So we start by having just a quick look. We've got coefficients of 1, -8, 55 and 150. Now you literally could guess and check values for z that would make this equation true until you found one. This could be a very tedious and time-consuming process. So particularly in an exam situation where time pressure is essential, I would highly recommend the use of your graphic calculator to find the first zero of this polynomial. So from the menu, move down to the equation app, then select F2 for polynomials. It's a third degree polynomial. We wouldn't expect more than a third degree in an exam because it's just too time consuming. Now we enter the coefficients: 1, -8, 55, 150. Once we have those done, we press F1 for solve, and straight away we get the zeros of the polynomial. The first one is the real number -2, and then the next ones, as we know from the from theory, they'll be complex conjugates. So we can now pretend that we found -2 by trial and error. We still have to show a bit of working to justify why that is a zero. So we'll say try z equals -2, and then evaluate. -2 cubed minus 8 by -2 squared plus 55 by -2 plus 150. Now technically we don't know whether this is true yet, so I suppose we should say left hand side equals this expression. Now -2 cubed is -8, -2 squared is 4, 4 times that is -32, minus 110 plus 150. Now we can see that this and this add to -40, -150, altogether that comes to 0, and so that does equal the right hand side of the expression. We've just managed to show that -2 is a zero of the equation. We therefore can claim from the factor theorem that z minus -2, in other words z plus 2, is a factor of our polynomial in z. Now, so far so good. The calculator gave us this. We do a quick evaluation to justify this statement. Now the fun begins. This is where we are going to use long division, the same long division from primary school, to divide this factor into this polynomial and see what we produce. So here we are, z plus 2 sits at the front. My polynomial, z cubed minus 8z squared plus 55 z plus 150. Now definitely take your time over this procedure. If we make one little mistake in this procedure, it will mess up everything that follows. It is definitely worth being a little bit slower and concentrating on getting this bit right. So we have two terms in our dividend here, and we have, our divisor, and we have 4 terms. Because there are 2 terms here, we'll just look at these 2 at a time. In fact, to make that even clearer that we're just going to look at them 2 at a time, I'll just cover those ones up so we don't even need to pay attention to them at the moment. Now, looking first at z, how many times would z divide into z cubed? Well, think of it this way. What is z cubed divided by z? The answer is z squared. So I'll put the z squared here, and then I multiply this by all of these. Z squared times z is z cubed. Z squared times +2 is +2z squared. And I subtract to see what's left. The first part comes to nothing. It must come to nothing. If this doesn't come to 0, we've made a mistake and we need to go back and check. Now this is where we need care. Negative 8 subtract 2 is negative 10 z squared. There are two parts to this. There's only one part here. We will have to move the next term down. Plus 55z. And we repeat the process. We think what would we need to multiply by z to get negative 10z squared? We'd need to go negative 10z. Negative 10z times z is negative 10z squared. Negative 10z times 2 is negative 20z. Once again we subtract. In fact, I might even put brackets here to remind myself that I'm subtracting both of these. So negative 10z squared subtract the same thing has to come to nothing. 55 subtract negative 20. That's the same as add 20, so I have 75z. Move down the last term, plus 150. Z multiplied by 75, positive 75. 75 times z is 75z. 75 times 2 is 150. We subtract both of these. This is nothing, this take this. The fact that we've ended with 0 means that this has worked properly. This has divided through the cubic polynomial, leaving a quadratic factor and no remainder. That's important. If we get to the bottom and there is something other than 0, we've got to go back and find the mistake that we made. So, our polynomial in z, the original cubic, equals 0. We now have that our polynomial is the same as z plus 2 multiplied by this quadratic. Z squared minus 10z plus 75 equals 0. Now, we're faced with the job of factorising the quadratic. Now, the quadratic is something that we have a few different processes, a few different techniques. I note first that the coefficient in front of the squared term is a 1. So the first attempt, I'll try to think of two numbers that add to negative 10 and multiply to 75. Now, multiplying to 75, I could think of things like 5 times 15. Because it's a positive 75, positive 5 and positive 15 aren't going to add to this. Neither are negative 5 and negative 15 going to add to this. I could keep trying a few more, but I realise from my earlier work on the calculator that the second and third root were complex numbers. I'm not going to find simple real number combinations here, so there's really no point bothering to think of them. I will, in fact, have to use the completing the square technique. So the plus 75 is just going to move out of the way. It's still there and it's still equal to 0. And I'm going to do a little bit of things in here to complete the square. In order to complete the square, we want to make sure that this coefficient is 1. It is. We divide this one by 2, so we get negative 5. We square that, and we add that at the end to make a perfect square quadratic. Now, we can't just add something in the middle of an equation for no apparent reason, so I have to immediately subtract the same thing. Adding and subtracting the same thing means that this all stays equal. Z plus 2. Now, looking at just the first three terms, that's a perfect square. My perfect square will be z minus 5. And then I've got a little bit to do here. Negative 5 squared is 25. Negative 25 plus 75 is plus 50 equals 0. Now I want to write this as something squared. I want to write this as subtract something squared, so that I'm having a difference of two squares here. Now the question becomes, what could I possibly square that when subtracted becomes 50? Clearly there would have to be a root 50 part to this, which we'll simplify in a minute. But there would also have to be the imaginary number I. Now root 50 squared would give me the 50. I squared is -1, so minus of -1 would make it positive. That's what I need. Whenever there's a positive here that we want to make negative, there's going to be an I appear inside this squared term. So we have z plus 2. Now the difference of two squares pattern. Z minus 5 plus root 50i, z minus 5 minus root 50i equals 0. And our factorisation is done. The last thing I'm going to do is simplify root 50. I recognise that that is the same as root 25 times root 2, so it's better expressed as z minus 5 plus 5 root 2i, z minus 5 minus 5 root 2i. Using the Null Factor Law, by inspection, we can see that if this term were 0, then z would equal -2. Now that's, of course, what we started with. We pretended that we did guess and check. Of course, the calculator gave us this result. So there's no surprise that we've produced the same term there, the same solution. Now, if z minus 5 plus -5 equals 0, transposing these constant parts, we would see that z equals 5 minus 5 root 2i. And the third term, z would equal 5 plus 5 root 2i. Again, if there is a complex solution, there will be a complex conjugate. They come in pairs. And if we check what the calculator told us, those, just make sure you can see them, those three solutions on the calculator are what we've just produced. That's how you solve cubic polynomials by long division and then completing the square. So the two important parts of this technique, the long division and what happened in here with completing the square.